Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. My name is Sava, and today we are continuing our discussion of heteroskedasticity tests, that is, statistical procedures that we can use to detect dependencies in the variance of the error term and some other factors. In the previous video, we have discussed and applied the Breusch-Pagan test for linear relationships between variance of the error term and the initial regresses of the model, and we discussed some of the limitations. That is, it assumes a particular functional form between the variance of the disturbance term and the regresses, and that if the relationship is indeed different, this test would not precisely capture what's going on. And today we are therefore discussing the second most popular test of heteroskedasticity, and the one that is initially taught in many econometrics courses. It has been developed many decades ago in the mid to late 70s by Goldfeld-Quandt, and therefore it's called the Goldfeld-Quandt test. Well, to apply it, we need to think about something different. We need to think about whether the error term, the variance of the error term precisely, is an increasing or decreasing function, or is dependent somehow on some of the regresses we have. Then we need to sort our data in increasing order as per some of the regresses, and then we need to separate our data that has been already sorted into three equal categories, and then we will throw away the middle part and estimate two separate OLS regressions on the top of our data and on the bottom of our data. And then we will be able to see what is the variance of the error term, that is the residual squared sum, the RSS, of those two partial regressions on the bottom third and the top third of the data, ranked again by the values of a particular regressor in an increasing order. And then we can use the F-test for the equality of variances to determine whether there are significant differences in the variance of the disturbance term, that is, in the RSS, in those two regressions, and conclude whether there is any heteroskedasticity present in that setting. The benefit that the Goldfeld-Quandt test has over the Breusch-Pagan test is that it has less stringent of an assumption what is the functional form of the relationship between the variance of the disturbance term and the initial regresses. However, it also has notable limitations. For example, when you throw away a bunch of terms in the middle of your sample ranked by a particular regressor, you can actually throw away the heteroskedasticity with those observations as well, which might be relevant. And also, again, it's relatively assumption sensitive. How much of your data do you throw away? By which regressor are you ranking the data, and so on and so forth. And some studies identify that the performance of this test on small samples is not really successful. But without further ado, let me show how to apply the Goldfeld-Quandt test in Excel and how to determine whether there is heteroskedasticity in the data in the less of a parametric sense than the Breusch-Pagan test allows. So first of all, we will need to rank our returns. We need to sort all three of our variables, that is the dependent variable, the return of the Tesla stock, the oil returns, and the S&P 500 returns, according to one of those variables. We can select one of the two independent variables we have, so we can either sort by oil returns or sort by S&P 500 returns. In our case, we suspect that the S&P 500 returns are more relevant indeed for the volatility of the Tesla stock, so we'll sort by those. But you can also sort by oil returns, and we're going to see how it changes the results or not. So to do that, we can actually apply one of the newest Excel functions that have been developed just recently, that is the sort function, that can allow you to sort the variables using a function instead of a traditional data sort framework. So we need to select the whole array, so those 3 columns and 1258 rows. Selected those, and then we need to apply the sort function, and then we need to sort the arrays of initial returns, so the Tesla, oil, and S&P 500 returns. Then we need to input by which array are we sorting. So we are sorting by the S&P 500 returns, so input 3 here, as it's the third column in the initial selection. Then we need to specify in which order are we going to sort. So we're going to sort in the ascending order, so input 1. However, it doesn't really matter for the test because the top and the bottom are used, and if you sort in a different order, then the top and the bottom will just switch. So it's not really important for this test, but just for the sake of simplicity, let's sort it in the ascending order. And then we need to specify, do we want to sort by row or by column? And here we are sorting by the row, so we need to input false, or the mathematical equivalent of false, that is 0. So then we press Shift-Control-Enter enforcing this formula, and we get our returns sorted by S&P 500 returns. As you see, the returns of the S&P 500 benchmark go from the lowest, minus 4.1%, to the absolute highest, plus 4.96%, and the returns of Tesla stock and crude oil are ranked accordingly. So first, we need to determine the total number of observations in our sample. To do that, we can just use the count function and apply it to any variable in terms of the array of this variable. We already know that there are 1258 observations, but it's good to be on the safe side. Now we need to separate our sample into 3 equal parts, throw away the middle, and carry out with 2 separate OLS regressions for the bottom third and for the top third, as ranked by the S&P 500 return. So we need to basically round down our total number of observations divided by 3, and we need to round it down to the nearest integer. And we see that we need to include 419 bottom observations for the first OLS regression and 419 observations for the second OLS regression. Then we can carry forward with these 2 regressions. So first we select again a 3 by 5 array and enforce the linest function. And here we need to select the first 419 rows. So to do that, we can easily apply this rule of thumb. We go from the very bottom, so R3 in terms of our dependent variable, and we need to move 419 rows below. As we include the starting row, we need to just add 418, so 1 less than 419. So we will move all the way down to R421. And then for the regressors, we need to select the equivalent number of rows. So from S3, we go to T421. That will select our dependent variable in terms of 419 bottom observations, and our regressors in terms of the respective 419 bottom observations. And then we select that the constant should be reported and that the additional statistics should be reported, and press Shift-Control-Enter. And here, what we are concerned with the most is this value in the bottom right, that is the residual squared sum, the variance of the error term for this subsample, which is equal to 0.28. And then we would need to compare it with the respective value of the RSS for the second regression that we'll undertake for the top 419 observations. So we select the same array, 3 by 5, apply linest, and now we need to go all the way down to R1260. So we need to start with a row that's 418 higher. So 1260 minus 418 is 842. We go all the way down to R1260. We can type it in or just click. And in the similar fashion, we go all the way from S842 all the way to T1260. And then we input 1 for the constant, 1 for the additional statistics, and again press Shift-Control-Enter. And we see that the RSS, the variance of the disturbance term, in that case is 0.29. Now we can apply the f-test for the equality of variances and determine whether this difference in variance, the ratio of the variance, is significantly different from 1. So we need to divide the greater of the two. So we can just apply the max function, or if you already figure out that this one is higher than that one, you could just type in as 1278, and then we need to divide it by the minimum of the two, the lower of the two. So we get a value of the f-stat that is greater than 1, greater or equal to 1. And we get 1.0352, and then we need to convert it into a p-value to figure out what is the probability that there is no heteroskedasticity in the data. So to do that, we need to apply the right-tailed f distribution, inputting the f-stat as our x, and the degrees of freedom would be equal to the degrees of freedom in the first and the second regression. But given the fact that we are only concerned with one tail of the test, because our f-stat couldn't be lower than 1 by design, as we divide the higher RSS by the lower RSS, we need to multiply this by 2. And we get 72.47%, which is comparable to the p-values we got for the Breusch-Pagan test. And it actually reinforces the claim that the probability that there is heteroskedasticity in the data is relatively low, lower than 30%, as this p-value is comfortably high. So in terms of the relationship between the variance of the disturbance term and the initial regressors, we can be ultimately sure that there is little to no relationship, and we can treat our errors as homoskedastic for now. That is, that the variance of those is comfortably constant, and our variance estimators for the coefficients of the regression are as low as possible. And that's all there is for the Goldfeld-Quandt test and the non-parametric or semi-parametric approaches to detecting heteroskedasticity. In future videos, we will discuss even more heteroskedasticity tests and dig deeper into the topic. Please leave a like on this video if you found it helpful. In the comments below, I am eager to see any of your suggestions on future videos on business, economics, or finance you would like me to make. And please don't forget to subscribe to our channel. Thank you very much, and stay tuned.